AI agent that runs flawlessly in a local demo. Deploy that exact same code to production and watch it collapse under real load. The demo agent looks solid, but it's a sandcastle. It stands up beautifully only because nothing is leaning on it. It faces zero real user traffic, zero server crashes, and zero intermittent network failures. When civil engineers build a physical skyscraper, they don't start by stacking glass and steel. They sink concrete piles hundreds of feet straight down through soft soil, anchoring the structure to solid bedrock before they ever build upward. Scaling an AI agent requires that exact same architectural discipline. To survive the chaos of production, you have to pour 3 specific, load-bearing software foundations beneath the agent's code. Skipping those foundations means any scale you add isn't actually growth. It is just stacking a heavier structure on top of a surface that is guaranteed to give way. The first foundation is durable state. When an agent executes a multi-step task, like calling a tool, reasoning about the output, and calling another tool, it has to keep track of its progress. This diagram illustrates the risk. In a local demo, the agent holds its progress in system RAM, shown here on the left side. If a server restarts or a machine crashes at step 9, that memory evaporates. The agent gets total amnesia and is forced to start over from 0, meaning you pay for the whole run twice. On the right side, we see the architectural fix, synchronous checkpointing. After every single step, the agent writes its complete state to a durable database, like Postgres or DynamoDB. Modern frameworks handle this out of the box. LangGraph 1.0 ships with built-in checkpointers, while tools like Temporal achieve the same result by recording and replaying an event history to rebuild the agent's memory. But durable state requires a strict partner, idempotency. Any step that touches the outside world, like charging a customer's credit card, must be designed so that if a crash forces the system to replay that exact step, the side effect is not duplicated. By pairing durable state with idempotent tools, a fatal process crash becomes a mere pause. The agent wakes back up and resumes at step 9, exactly where it left off. Internal crashes are only half the threat. The second foundation, error handling and recovery, deals with the outside world, API rate limits, timeouts, and dead downstream services. If you assume the happy path and expect every external call to succeed, a single downstream timeout at step 9 will throw an exception and send the entire 12-step task into the trash. This flowchart breaks down a layered recovery strategy to absorb those failures. The first layer handles transient errors, the temporary hiccups. Instead of failing immediately, the system retries the call using exponential backoff, waiting increasingly longer, 1 second, then 2, then 4. You also have to add jitter, a small amount of randomness to that wait time. If 1,000 agents hit a rate limit and all retry at exactly 2 seconds, they hit the recovering API in one synchronized wave, a thundering herd that knocks it right back offline. Jitter spreads them out. If a dependency is completely down, retrying is a waste of time and money. That triggers the systemic layer, the circuit breaker. It trips open, failing requests instantly to protect the system until the service eventually recovers. The final 2 paths handle complex failures. Compensation uses a saga pattern to actively undo a previously committed action, like canceling a flight booking if a later step fails. Graceful degradation keeps the agent alive by falling back to a cheaper model or returning a partial answer. These 4 layers act as shock absorbers. Intermittent failures are categorized and handled, allowing the architecture to sway under pressure instead of snapping. The final foundation, testing at scale, addresses a problem unique to large language models. They are inherently non-deterministic. Traditional pass-fail software testing relies on predictable outputs. Give an agent the exact same input twice, however, and tomorrow it might take a completely different path of tool calls than it did today. A basic health check will show a 200 OK status, while the agent confidently does the wrong thing inside. To catch this, engineering teams use trajectory evaluations. Using benchmarks like Tau2Bench, you simulate multi-turn conversations and judge the entire sequence, evaluating which tools were selected, in what order, and with what arguments, rather than just grading the final answer. Tracking those trajectories requires deep observability. By adopting the Open Telemetry Gen A conventions, developers record step-level traces of every token, every tool call, and latency spike.
You cannot fix a failure you didn't record. Once everything is instrumented, you run a secondary LLM as a judge over your live traces. When you find failures, you mine them into a permanent regression suite, ensuring that a specific, silent mistake can never slip into production unseen again. This overview illustrates the reality of scaling. The code inside the agent on the left is exactly the same as the code on the right. The difference between collapse and scale is entirely dictated by the infrastructure placed underneath it. The Sandcastle on the left runs memory and RAM that washes away in a crash. It expects a happy path, so a single failed API call kills the run. And it relies on manual testing, meaning it breaks silently in the dark. The skyscraper on the right rests securely on 3 interlocking layers: durable state to survive crashes, a layered resilience strategy to absorb external failures, and a trajectory-based testing suite to catch non-deterministic errors. Scaling an agent is not achieved by buying a bigger model or writing a cleverer prompt. It is achieved through the invisible, structural engineering beneath the surface. Before you scale up, you must dig down.